Hello. For our EEE 185 course project, the topic we chose was millimeter wave and terahertz communications for future mobile networks. My name is Cynthia Laboret.
My name is Shazay Balmer.
My name is Christian Zatello.
And my name is Ben Hero Roman.
So shown here is our table of contents. This will be the order of our presentation. First is the introduction, second is the problem, third is the literature survey, fourth is approach, and lastly, the fifth being our summary of results. So moving on, we will begin with the intro about millimeter wave and terahertz communications. So as mobile networks continue to evolve, two promising technologies are millimeter wave and terahertz communications. These high-frequency wireless communication technologies hold high potential to revolutionize future mobile networks, offering unprecedented data rates and enabling a wide range of innovative applications. Now I'll be passing it on to Christian.
Thank you, Cynthia. Next is our problem. Here we'll have the millimeter wave and terahertz communications as the still emerging technologies. So there's a variety of problems with this topic, such as signal propagation and range, penetration and blockage, device and system complexity, power consumption and energy efficiency, and cost and redeployment.
Hey guys, in this next section, we'll cover the literature survey, which is the analysis and discussion of these problems. With the first problem, signal propagation and range, we see that millimeter and terahertz waves have shorter wavelengths, and because of this, they're more susceptible to attenuations and more easily absorbed by atmospheric gases, and signal blockage is more pronounced, especially in dense urban environments and over long ranges. The second one is penetration and blockage. These waves also have limited penetration capabilities, and because of this, they can be blocked by almost anything. And it's not limited to just static objects with moving objects as well, especially in high-speed scenarios like using your phone on the move in a car. And the third, device and system complexity. These waves require sophisticated hardware components and complex signal processing algorithms in order to function, which means it requires a lot of investment and a lot of work required to make these algorithms. They need efficient transceivers, antennas, and base stations, and they must support multiple input, multiple output. Fourth, power consumption and energy efficiency. Because these waves require more power, that obviously means they require more energy, and that consumption increase also reduces battery life, especially for mobile devices where it's crucial. The balance of this power consumption and energy is crucial for sustainable operations. And these main problems include with the base stations and mobile devices. And for cost and redeployment, the waves require substantial infrastructure investments. There's also difficulties with regulations and spectrum availability for companies trying to output these waves. And the higher frequency bands means that there's a higher need for a dense network of base stations and smaller cells due to their limited range. And the significant initial investment is quite substantial, as well as overtime costs due to maintenance, licenses, and other upgrades. I'll be passing the mic back to Christian.
Okay, so next is a fun little quote we found, which is information and communications technology unlocks the value of time, allowing enabling multitasking, multi-channels, multi-this, and multi-that. Next is our approach, and we'll be mentioning the challenges ahead. So for the approaches, we have a variety of solutions to the challenges we mentioned. First is spectrum allocation. Second is signal processing and modulation techniques. Third is network security. Fourth is interference management. And fifth is terahertz transceiver technology.
So for our first approach, we have spectrum allocation. So for millimeter wave communications, these frequency bands typically range from 30 gigahertz to 300 gigahertz. And it is also important to understand that governments and regulatory bodies play a crucial role in allocating the necessary spectrum for millimeter wave usage. This involves the spectrum sharing technologies between different systems in the same frequency band. Moreover, techniques like interference coordination and frequency domain resource allocation help mitigate interference and help improve energy and efficiency. As for terahertz communications, they also function similarly, where the government must also allocate the dedicated spectrum resources, considering the factors such as interference mitigation. As for its frequency bands, it typically ranges from 0.1 terahertz to 10 terahertz. Some techniques for this type involve database-driven spectrum management, allowing more efficient utilization of limited terahertz resources. And now passing it back to Ben.
Thank you, Cynthia. So for our second approach, we'll be talking about the signal processing and modulation techniques. So it is an efficient terahertz band signal processing must account for the use of ultra massive MIMO, or it stands for multiple input, multiple output antenna systems to overcome the very short communication distance due to severe power limitations and propagation losses. This signal processing must also overcome the mismatch between the bandwidths of the terahertz channel and the digital baseband system. Modulation techniques such as coding for error correction, equalization algorithms to multi-path propagation can be useful. Error control coding is essential for error detection and correction, which enhances the transmitted data and mitigates the effects of interference. Another technique also involves the equalization and channel estimation, which shows the high frequency dependent channel impairments. Equalization techniques gives the feedback or maximum likelihood detection to restore the transmitted signal. Channel estimation technique involves the compressed sensing, and machine learning can be applied for detection and estimation in order to handle the unique propagation characteristics. Now I'm passing it to Shah Zaib.
Thanks, Ben-Hur. Network security. Security and resilient networks allow for frequent spectrum reuse and multiple MIMO systems in a limited space. And to secure lower frequency communications, the physical security of the infrastructure, including base stations, network equipment, transmission facilities, and a decentralized wireless network, is required. Security mechanisms must be ensured to prevent signal interruption during beamforming. And another essential is secure algorithms to protect against signal manipulations in millimeter wave communications.
Thank you, Shazib. For our fourth solution would be the interference management. Due to how narrow the beamwidths and high antenna gain are, an advanced interference management technique is essential to implementing the mitigation of any effects and also improving network performance. This involves beamforming coordination, which allows the focus of a transmitted signal to go along a specific direction. Massive antenna arrays with beamforming techniques can be used to overcome high propagation loss, reduce interference, and to also deliver high network capacity with multiplex transmitters. Adjusting the dynamic resource can be employed to allocate the frequency or power on a radio resource. This can be adjusted towards the interference conditions and can also be matched effectively, and also the system performance can be optimized.
Thank you, Ben-Hur. Next, in our final solution, is the terahertz transceiver technology. An efficient and compact transceiver that is capable of generating and also detecting terahertz signals comes along with an antenna design suitable for the terahertz frequency range coverage. This is used for the terahertz radiation and reception, as well as increasing the radiated output power through the integration of many oscillators with dedicated antennas. Some technologies also involve the analog beamforming or phase array in the transmitter and receiver, which allows for a better suppression of interferers and reduced signal processing. In combination with multiple transceiver chips to realize the complexity of an MIMO system with many channels is a cascading of integrated circuits. This technique enables the manufacture of identical chips of smaller size and hence the higher yield at a lower cost.
And to conclude, here's our summary of results. To reiterate, these were our challenges and solutions, and ultimately further research and development are needed to advance these technologies and address their challenges for their successful deployment in the future. And here's our citations of the resources used. Thank you for listening.